Hello, my amazing students. You are welcome to my class today on electrochemical cells. So the question now is, what is an electrochemical cell? An electrochemical cell is defined as a device that is capable of generating electrical energy from chemical reactions, or a device that uses electrical energy to cause chemical reactions. Electrochemical cell is divided into two: electrolytic cell and galvanic cell. Galvanic cell is also called voltaic cell. The electrolytic cell was dealt with in SS2 class, and the image I have here is on the electrolytic cell. If you look at the image, you find out that a power is needed, which is a battery that generates electrical energy as a result of the chemical reactions that took place in the battery. Now, this electrical energy is used to decompose the molten sodium chloride to produce sodium atom and chlorine gas. In other words, the electrolytic cell is used to produce chemical reactions. But this chemical reaction is activated by the electrical energy that is generated by a battery, which is the source of power. So in today's class, I'm going to center more on the galvanic cell, which is also called the voltaic cell. You can see it's quite different from the image of electrolytic cell. A battery is not required. In fact, in itself, it is a battery. Chemical reactions took place in the voltaic cell to produce electric current. And how do we know that electric current is produced? A voltmeter is used. The deflection of the voltmeter indicates that current is produced. However, a galvanic cell has two half cells: the oxidation half cell and the reduction half cell. The oxidation half cell is also called the anodic half cell. The half of the cell where we have loss of electron. The zinc metal, which is higher in ECS and more reactive than copper, loses 2 electrons to form zinc ion. While at the cathodic half cell, where reduction takes place, which is gain of electron, the copper 2 ion accepts 2 electrons to form copper atom. And the two half cells are joined together by salt bridge. The salt bridge can contain different salts, but in this case it's potassium chloride. It can be potassium nitrate, it can be sodium nitrate, it can even be sodium sulfate or even ammonium chloride. When both are connected externally using wire and connected to a voltmeter, the deflection of the voltmeter is a proof that current is produced. So we can have an overall reaction of Zn plus Cu2 plus to give us Zn2 plus Cu. Then the cell notation is represented as Zn/Zn/SO4//CuSO4/Cu. The slash represents the salt bridge. It can also be represented with a single broken line, while the single slash indicates the boundary phase between the electrode and its electrolytic solution. I'm going to leave you with a video of galvanic cell, where a thorough explanation and a picture of how these electrodes lose electron and how the copper ion gains electron at the cathode Watch the video and I will come back at the end of it to continue.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution, and the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a voltmeter to the cell shows that electrons flow from zinc to copper. The voltmeter reads 1.103 volts. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Let's talk about the types of the galvanic cell. The galvanic cell will have two types, the primary cell and the secondary cell. The primary cell are those galvanic cells that are not rechargeable. They are not rechargeable because the chemical reactions taking place in them are irreversible. Examples of galvanic cell include the Daniell cell and the Leclanché cell. The Daniell cell consists of a zinc rod in zinc sulfate solution as the anode, then a copper rod in copper 2 sulfate solution as the cathode, with a porous pot which serves as the salt bridge in separating them. As usual, the zinc, being higher in electrochemical series and more reactive, loses an electron to form zinc ion, while the copper 2 ion gains an electron to form copper atom. For the Leclanché cell, it also consists of zinc as the anode, but the cathode is a graphite rod, which is an allotrope of carbon, the only allotrope of carbon that conducts electricity. Then ammonium chloride is taken as electrolyte, while manganese 4 oxide serves as the depolarizer. The secondary cell is another type of galvanic cell, but this type of galvanic cell can be recharged. They can be recharged because the electrochemical reactions that take place in this particular cell can be reversed. So the reactions in secondary cell can be reversed, and these reactions that generate electricity which can be reversed makes secondary cell to be rechargeable. So secondary cell is a galvanic cell that are rechargeable. Examples of secondary cell include the lead acid accumulator, which is the car battery, the nickel cadmium battery, the lithium ion battery, the nickel ion battery. These are examples of secondary cells. Now let's look at the differences between primary and secondary cells. The primary cells are not rechargeable, while the secondary cells are rechargeable. Also, the reactions that take place in primary cells are irreversible, while the reactions that took place in the secondary cell that result in the generation of electricity or electrical energy are reversible. Now I'm going to leave you with a video of galvanic cell, precisely the primary cell.
Hello guys, in this video we are going to discuss some applications on galvanic cells. A voltaic cell can be primary or secondary. In this video we are going to discuss the primary cells, and in the next videos we will discuss the secondary types. Primary cells are not rechargeable and are discarded after they run down when all the chemicals are used up. In other words, no more chemical potential energy available, or the chemicals in the battery can react to produce electrical energy. Here I go the illustration of what happens to the primary cell. The anode loses electrons to the cathode, and both connected by a wire. Here the cell generating electrical current, but when the battery is run out of reactants, and almost they all turn it into products, the cell stops working and it can't be recharged again. So here is an example on primary cell, which is dry cell. Dry cell battery is a voltage producing battery containing the electrolyte chemical in the form of a thick paste. It produces voltages of about 1.5 volts. In this diagram, which represents the parts of a dry cell battery, the zinc casing provides enclosing to the electrolyte and the cathode as a whole. Ammonium chloride is the electrolyte used in this type of battery. Just ahead of the electrolyte lies a manganese dioxide, separated from the electrolyte by a separator. At the center of the cell battery lies a carbon rod, which is the cathode, and zinc casing is considered as the anode. So let's understand how it works. Every portion of the battery device has chemical reactions occurring within. While a reduction reaction occurs at the carbon electrode, oxidation proceeds at the zinc casing, which is the anode. The chemical reactions that define the entire energy process are as follows. At the anode, zinc loses 2 electrons and is converted into zinc 2+ ion. The ammonium ion from ammonium chloride reacts with the 2 electrons to produce ammonia and hydrogen gas. The manganese dioxide near the cathode reacts with hydrogen gas liberated to form manganese 3 oxide and water. Combining equation 1 and 2, we get the following equation. And combining all the above equations, we get. Due to these reactions, chemical energy gets converted into electrical energy. This energy then flows from the battery to the connected device through the outer circuit. So guys, here is a total recap of what we've learned today. Primary cells are used once and can't be recharged again.
You are welcome back. Let's look at the differences between galvanic cell and electrolytic cell. The anode is a negative electrode in galvanic cell, but in electrolytic cell, the anode is a positive electrode. Also, the cathode is a negative electrode The cathode is a positive electrode in galvanic cell, while the cathode is the negative electrode in galvanic cell. Now let's look at the differences between galvanic cell and electrolytic cell. In the galvanic cell, the anode is a negative electrode, while the anode is positive electrode in electrolytic cell. Also, the cathode is a positive electrode in galvanic cell, but negative in the electrolytic cell. However, oxidation takes place at the anode, whether it's for galvanic cell or electrolytic cell, and reduction takes place at the cathode, be it a galvanic cell or electrolytic cell. In electrolytic cell, a source of energy is required, while in galvanic cell, energy source is not required, and that makes the reactions in galvanic cell spontaneous and non-spontaneous in electrolytic cell. Here is where I'm going to stop for today, but I will advise you to read up what we'll have next, which is catalyst and catalysis. Catalysis are catalyzed reactions, reactions that require catalyst, reactions that certain substances will be added to them, either to increase the rate that reaction is taking place or to decrease the rate the reaction is taking place. So, read it up and get ready for my next class. Until then, bye bye for now.